Welcome to Ask and Learn.
We're told that we have a rigid metal bar here that uses a switch. It's supported by a spring here and a spring here, and then there's an applied load here, and then there's a contact down here that will close the switch. We have the gap in this contact is 10 millimeters, and then the distance here between this and this is 50 millimeters, and then this and this is also 50 millimeters. So what I did is I just kind of used basically just some algebra. I said, okay, well this bar defines a line, and if I say this is my origin of my x-axis, so let's put that in there, and then I'm going to measure y down just for convenience here. Then this bar is described by a line where there's some displacement at x equals 0, and then it has a slope that we will need to determine. So if we want this to touch the contact here, then we need this thing to go down 10 millimeters. So y at 100 millimeters, so that's distance, is y naught plus 100 m, our slope, and that has to be plus 10 millimeters. So again, I'm measuring positive is down. And then we also need to know what this displacement is at this point, because we need to know what the spring load is. So the displacement at 50 millimeters is y naught plus 50 m, and we'll just kind of call that y sub b. Now we also know that the force in spring A here is the spring constant times y naught, so that's the displacement there. And the force in spring B is minus kb yb, and I guess I should probably describe why it's a minus. So if we draw a free body diagram of the spring, then we have an equal and opposite force acting on the spring here from FB, and then obviously on the other side from ground, we have an equal and opposite force. And then this side is grounded, so it doesn't move. And then this side, I've said positive is in this direction, is down. So we can see here that we need a negative sign, because positive direction for the force is up, positive direction for the motion is down. So if we put a positive force on here, we'd expect, or if this displacement is positive, then we'd expect the force to be in the other direction. So that's why we have a negative sign here. If we sum moments, and say that at some moments about point B here, then we just find that FC, this force here, the applied load, is equal and opposite to FA. And then summing forces just in the vertical direction, we find that FB must equal FA minus FC. And then using this result, that means FB must equal 2FA. And now we can use our spring equations, and we find that F minus FC equals K, the spring constant in the one spring, times y naught, displacement of this spring, and then minus 2FC equals minus KB times YB. And then we know y naught plus 100m equals 10, and YB plus equals y naught plus 50m. YB equals y naught plus 50m. And so we can, again, use these equations here to get y naught, and try to solve for YB, and then plug those into here and here, and we get an equation for FC. And again, well, FC and M. So we could figure out what M is, but we're not asked to do that. So if we just crank through the algebra of these two equations and two unknowns, we get that FC equals 10 times Ka times KB all over 4KA plus KB. And if we plug in the values that were given, that both of these spring constants are equal, and they both have a constant of 5 newtons per meter, then we find that FC, to close the gap of 10 millimeters, has to be 10 millinewtons.